Okay, so I'm Ben Moran at Google DeepMind and the robotics team at London. Our previous projects I've been working with over the last couple of years have been lots of real robots. So you saw the OP3 soccer robots, this work. And the interesting thing here was it's trained entirely in simulation. It's 0 shots into real. So although there was a lot of work that went into the RL and the game design and the reward design and the rest of it, the interesting thing to me is that all the information we needed to learn these behaviors was just in the simulator. The rest of the learning process is really how do we extract that information from the simulator to the real world so we can run it on the robots. And we spent a lot of time thinking about how to do this transfer. So there, the work is really like how do you find the right settings that to the simulator that enable us to run in real like this. But there's no actual transfer back. So if the robot runs and it falls over, we don't learn anything about that except via the minds of the experimenters, twiddling the parameters. So it's a very slow and error-intensive process. Just to underscore this whole like simulation is all you need in this dexterous manipulation work here, there's actually no learning algorithm at all. It's entirely Majoko running in real time with the planner rollouts. And so literally the simulation contains all the information you need to do this rich behavior. So obviously the question is, how do you find the parameters to match this? As I've said, at the moment, we pick some parameters, we learn some behavior, then we try it in real and like hope for the best. And then it's the experimenter who provides this bridge back. But of course, we've been through this in sort of 2014, 15, or this hand engineering of features, and we know perfectly well that the best way to tackle this problem is to use gradients and back propagate where you can. But the problem with applying this like conceptually simple approach is that we have all these pieces to get through. We have to think, how are we going to render it? What loss functions do we want? How are we going to differentiate with respect to the pixels? How are we going to differentiate with respect to the physics? This all seems quite difficult, and that's perhaps why people haven't done it very much until now. But it turns out that all the pieces are already there, and they're already kind of easily available in open source. So within just Google, we have, and externally shared, we have Majoko, which now has the NJX JAX implementation, which is differentiable and accelerates and works with JAX. And we also have Differen, which is a JAX-based differentiable mesh rasterizer. And you can also use Gaussian splatting. I've seen lots of papers at this conference using Gaussian splatting for the same thing, of differentiating parameters with pixels with respect to parameters. So the interesting thing for me is that you can then take this off the shelf, and because NJX works with existing Majoko models, which we've already tested very extensively and we know can transfer to the real world, they capture all the nuances that we care about. It's possible to take our existing models without really any changes, run them in this new setup, and it runs fast enough, it's kind of real time and I can interact with it. So that's encouraging. And then the sort of more exciting thing, I think, is now we can differentiate from pixels right back through to any part of the Majoko simulation itself. So here we're taking, this render is of the Sawyer robot model that we had rendering the normals. And I can differentiate that with respect to any of the generalized coordinates in Majoko. So the positions and orientations of the blocks, and also the kinematic links in the arms. And you can see it knows an awful lot about how changing a particular parameter is going to say move the thumb grip or in what direction it will move. Did some just toy experiments really. It's very early days for this work, but I'm very excited about the potential, what we can do with it. So this is fitting like object poses and field of view, I think, using depth maps as the supervision signal. So we can fit like these multiple parameters at this. Oh, yeah, so moving 6 degrees of freedom, so position and orientation of the cube and the field of view of the camera. And then I think somebody also already mentioned this as well. Compared to pure computer vision approaches that just try to match images, we also have access to the full physics state. So we can, for instance, supervise on other signals that Majoko knows about, like contact penetration distance, so that we can ensure that the block's actually not penetrating into the floor. We've got things like the potential energy, so we can tell if things are floating. There's a lot we can do with that. And finally, sort of putting all this together, it comes back to my original problem. If I've got a decent Majoko simulation of my robot in the environment, I know it's not too bad, but it's also not going to be perfect. Like every robot will be slightly different. Maybe the cameras have been knocked in each cell. Maybe we haven't done all of the slow work with QR codes to calibrate everything. Maybe the illumination is a little bit off between my my simulation and the real world. And we can fit all of these things at once. So, for instance, in the robotic gripper that we have here, I have good joint proprioception for all the degrees of freedom except for the thumb, which is unactuated and unsensorized. So if I just take the ROS bags, I can't actually restore the full state. But now I can like fit this extra unmeasured degrees of freedom just from the video. My camera's been knocked, I can tilt it and reorient that back. And I can do this continuously with from just passive data without having to do separate collections. And then if you optimize all of these things together, you can do like quite large, probably hundreds of degrees of freedom quite easily. So at the moment, we're still stuck with this kind of local gradient-based local refinements only, but I think it's super interesting to think about where we can take this beyond that. So thank you very much.